Okay, Assalamu alaikum. This is Talha bin Ali, and today I'm recording the third and the last video of for the topic of combustion and combustion chambers. In the last two videos, recorded videos, uh, we have uh, we have basically studied the basic concepts of the combustion, and we in fact studied the stages of combustion in SI engines and CI engines in quite some details, and we also studied the phenomena of knocking in SI and CI engines, and we also had a brief overview regarding the variables which affects the knocking as well. And in the last after completing the combustion portion, we had a brief overview regarding the combustion chambers as well, and we basically studied the uh, different classifications, different configuration, different arrangements of the combustion chambers for SI engine, and I also gave you a brief overview regarding the different types of a combustion chamber in CI engines, which were basically direct injection combustion chamber and indirect injection combustion chambers. Uh, so, in the last class, we basically concluded the theoretical section of this chapter, and today I am going to start off with the numerical portion of this topic. So, starting off with the first question, and it is of and here you can see that in the book which we are following, that chapter number is 12 for the combustion and combustion chamber, but here the numerical questions are question number 15.13 and 15.14. So uh, this these questions are not from the book, from the textbook which we are following. uh, these questions are from the book of Sengel and Bowles of thermodynamics. So you don't have to worry about it, because I will provide you the questions. I will provide you the PDF of these questions, so you don't have to worry about it. Now, starting off with the first problem, here you can see that we have a methane, and methane is burned with stoichiometric amount of the air during a combustion process. It means that, for example, if I basically write this equation, I can write it as I have methane, and methane is added with oxygen. In fact, instead of using the oxygen, I will use here like this. And here you can see that this is the amount of the air, and as let me just complete this equation first. I will further explain this part. Now, uh, as a result, we will get some carbon dioxide, CO2, plus we will also get the water vapors as well, and you will note that we will get the two molecules of the water vapor if I balance the equation, and after that you can see that I will get the amount of the nitrogen molecules as well. So since I do not know the amount of the air which is going to be utilized here, and it is mentioned in the question that the amount is basically the stoichiometric. The air is stoichiometric. This methane is being burned with the stoichiometric amount of the air. So I'm just using here ATH. ATH is the number of moles which are theoretically required, number of moles of air which are theoretically required for the combustion of the methane. So here, and I will have to add this ATH here as well. Now the question here which arises is that how basically did we get this 3.76 moles of nitrogen? So the answer to that question is basically, for example, if um, we have 21% of oxygen in air. We have 21% of oxygen in air, and we have 79% of nitrogen, 79% of nitrogen in air. So uh, if I divide this 79, if I take the ratio of this nitrogen molecules, I will get this 3.76, that for every 1 mole of oxygen I will have 3.76 moles of nitrogen, and it is, that's how I have got this uh, for 1 oxygen there I will have to add 3.76 moles of nitrogen. This is the composition of the air, and it is based on this this composition that in air we have 21% of oxygen and we have 79% of nitrogen. Obviously there are some other gases like carbon dioxide and carbon monoxides in the environment as well, but we will not consider those gases, because as the amount of those gases are almost negligible. So we are not considering those gases. We will only consider oxygen and nitrogen in the air for the simplification of the combustion process. So this will be the equation for the question number 1, that methane is burned with the stoichiometric amount, which is ATH, and this is the 1 molecule of oxygen, O2 plus 3.76 molecules of nitrogen, and as a result I will get 1 molecule of a carbon dioxide and 2 molecules of water vapors, and I will get 3.76 times of ATH molecules of nitrogen. So starting off with the solution, here you can see that I have also mentioned the equation here as well, which I explained earlier. Okay, now after this will be the first step which you guys will have to perform, that you will have to write the combustion equation for this reaction, for whatever the fuel particle, for whatever the fuel molecule which has been given to you, either it is methane, or you have a propane or any other fuel molecule as well. After forming the balanced equation, the next step is basically the balancing of oxygen. Now here you can see that the balancing of oxygen can be done in 2 ways. Either if you balance the oxygen molecule, and number 2, if you balance the oxygen atom. Now that is totally up to you. I have solved some questions by balancing the molecule of oxygen, and I have solved 1 or 2 questions um, by balancing the oxygen atom as well. Here, as I have solved those questions by considering the atoms in which I have the oxygen molecule in the fuel, like if I have the oxygen molecules in even numbers in each of the product, I can balance the oxygen molecule. I can balance it in the form of oxygen molecule, but I can also balance it in the form of oxygen atom as well. So I have utilized the balancing of oxygen atom when I have a single atom of oxygen which is being utilized in the fuel particle. I think that was question number 15-19 maybe, or maybe 15 dash let me just check it. 15-19, yes. I have utilized this arrangement of the balance. I have utilized that method of oxygen atom balancing where I have this oxygen in the fuel, but that is no there is no hard and fast rule regarding this. You can either balance with the oxygen atom and you can balance it with the oxygen molecule as well. So now coming back to the question. Now coming back towards the question, here you can see that you have to assume the complete combustion. That it means that there will be the no formation of the carbon monoxide. We will have only the formation of carbon dioxide. We have to determine the air fuel ratio and the fuel air ratio. So this is what we have to do. We have to determine the air fuel ratio and the fuel air ratio. So basically if we determine the air fuel ratio, we can simply just reciprocate it to determine the fuel air ratio. And in order to determine the air fuel ratio, what we need here is we need the mass of the air and we need the mass of the fuel which is being utilized. Now after the formation of the equation, I'm going to balance the oxygen. As I mentioned earlier, as I explained earlier, in this question I'm going to balance the oxygen molecules. So here you can see on the left side of the equation, I just have a methane molecule. It means that there is no oxygen molecule. While here I have 80H moles of oxygen. So in the left side I have mentioned ATH. This is the theoretical, or you can say the stoichiometric amount of the air which is being utilized for the combustion, as it is mentioned in the question that you have a stoichiometric amount of the air. Now this is all about the left side, that we have only ATH molecules of O2. If we come towards the right side, here you can see in the formation of CO2, you can see that we have 1 mole of oxygen, 1 molecule of oxygen. Here we have O2. So here I have mentioned the 1 molecule, and if I move forward towards this 2H2O, the water only has 1 molecule of oxygen, but we have 2 molecules of water. It means there are 2 atoms of oxygen. So I can write these 2 atoms in the form of a molecule. So I have mentioned here the 1 molecule, and in the nitrogen we do not have any oxygen here, because all of the oxygen of the air is being utilized in forming the carbon dioxide and water vapors. So this is the oxygen molecule balancing. We will simply add it in order to get the ATH, which is coming out to be 2. Now the question is, what if I balance the oxygen atom? Now if I am balancing the oxygen atom, now here you can see oxygen balancing. On the left side, here you can see I have 2 atoms of oxygen. So instead of just writing the ATH, if I were balancing the molecule, I would have simply written the ATH. But here I am balancing the oxygen atom, so I will write 2 times of ATH, because I have 2 atoms of oxygen. Whereas if I talk about the right hand side, here you can see I have 2 atoms of oxygen in the carbon dioxide. So I'm not going to write it the 1 molecule. Instead I will write it as of 2 atoms of oxygen. Similarly here I have 1 oxygen in 1 water vapor molecule and the second oxygen in the second water vapor molecule. So again I have 2 oxygen molecules here. So the equation would have become like this, and we would have solved it to get the value of ATH. Again that would have come out to be 2. So it doesn't matter either if we balance the oxygen atom or if we balance the oxygen molecule. So okay, now coming back towards the solution, I have explained both methods of either balancing the oxygen molecule of or balancing the oxygen atom. Now the next step, the first step was the formation of the equation, then the balancing of the oxygen and determining the unknown variables in this equation, which we have mentioned earlier. Now the third step is basically the formation of the uh, balanced equation. Means we will substitute the unknown variables which we have determined. So I will substitute the ATH, the value of ATH in the above written equation. Now the equation will become CH4, and instead of writing ATH here, I have mentioned 2. Then O2 plus 3.76 times of nitrogen. Moving forward, I have carbon dioxide and 2 molecules of water vapor. Then I had 3.76 times of ATH. So now if I multiply this 3.76 with ATH, which has the value of 2, I will get 7.52. So I have 7.52 moles of nitrogen atom. So now I have obtained the equation which is completely a balanced equation, and there are no unknown variables, there are no unknown moles in this equation. Now moving forward, as it was mentioned in the question that I have to determine the air fuel mixture. So in order to determine the air fuel mixture, I explained earlier as well that I have to determine the mass of the air and I have to determine the mass of the fuel as well. So this is very important step and is needed to be understood very carefully here. Now here you can see that in order to determine the mass of the air, what I have done here is I have simply multiplied the number of moles of the air with the molecular mass of the air, and it is one of the basic formulas which all of you must have used in the intermediate level of the chemistry, that the number of moles is basically equal to the mass divided by mR, which is basically the molecular mass of the of air in our case. So when I am going to rearrange this equation, I will get mass is equals to moles multiplied by mR, which is the molecular mass of air. So this is what we have done here. We have simply, instead of writing a mass, I have written down the number of moles and the molecular mass of the air. The molecular mass of the air is 29 grams per mole, or you can say kilograms per kilomole. So in the book we have used the units of kilograms per kilomole, so I have just also written down the I have also used the units of kilograms per kilomoles, but you can also use the grams per mole unit as well. And here you can see that in the number of moles, you can see that I basically had this ATH, and how many moles or how many molecules of gases are present in air. So it is basically one molecule of 1 mole of oxygen and 3.76 moles of nitrogen. So the overall moles will become 4.76, and then these 4.76 moles is going to be, this 4.76 moles is going to be multiplied with the 2 as well. So the overall moles will become 2 multiplied by the 4.76 kilomoles. So again, since I had used the unit of kilogram per kilomole, so I will use the unit of kilomoles here. But instead, if I had used the unit of gram per mole, I would have simply used the unit of mole here. This is how we are going to get the amount of the number of moles, the mass of the air, uh, by multiplying the number of moles with the molecular mass. And in the denominator, you can see we have to determine the mass of the fuel, and we have simply the mass of the fuel. Here you can see we had just 1 mole. We do not have to write the mole here, since the mole of the fuel is just 1. All we need to do is we have to calculate the molecular mass of the fuel, which is since we had 1 molecule of a carbon, 1 atom of a carbon, so 1 multiplied by carbon plus 4 atoms of hydrogen. So 1 multiplied by 1 is the molecular mass of hydrogen and 4 is the number of atoms. So when we calculate it, we will get the value of air fuel ratio, and it is coming out to be 17.3 kilograms of air per kilograms of fuel. Air fuel ratio is basically a dimensionless number. So since in the numerator we had basically kilogram, we had air, so I have written down the kilogram per air, and in the denominator I had fuel, so I have written down kilogram per fuel in the denominator. But overall, the kilogram and kilogram would be cancelled with each other, and this is a dimensionless number. The next part was of calculating the fuel air ratio, and as I mentioned earlier, that fuel air ratio, all we needed to do was simply to calculate the air fuel ratio, and we will just reciprocal it to obtain the value of the fuel air ratio, and that is what we have done here. In order to calculate the fuel air ratio, we have just taken out the reciprocal of air fuel ratio. So the fuel air ratio would come out to be 0.0578 kilograms of fuel per kilograms of air. I hope you guys would have understand this question very carefully. I have spent some time on the first question because all the other questions are similar to this method, and there are not so many differences in the next questions as well. So if you have understood the first question very carefully, you will not face any problem in the next questions. Now moving forward, next we have question number 15.4, and here you can see we have burnt propane, but here the propane is burned with the 75% of excess air. So this is the main difference between the first question and the second question. In the first question, the methane was burned with the stoichiometric amount of the air, but here the propane is being burned with the excess amount of air, and the air 75% excess amount of air. Now assume the complete combustion. You have to determine the air fuel ratio. So this is what the main difference between the first and the second question is. Now moving forward, as I explained earlier, that the main difference between the first question and the second question is because of the excess air which is being provided in the second question. So the equation for the first thing which you need to do here is you have to basically form the chemical equation, and in order to form the chemical equation, we are going to just I'm going to help you write down this equation, because you have to form this equation if these questions appear in the exams. We basically had a propane, and this propane was burned with the air, which is O2 plus 3.76 moles of nitrogen, and as a result we would have got CO2, and we would have also got H2O. Now what here needs to be understand is, for example, if the propane would have burned in the stoichiometric air, so I would have written down the ATH moles of the air. But here, as it is mentioned that the fuel, that the propane has been burned with this 75% of the excess air, so instead of just writing the ATH, I will add 1.75 times of ATH. It means that we have some excess air, some 75% of excess air. We have provided the excess air for the combustion process. Okay, now if I balance this equation, I will put 3 here and 4 here, and again here you will see that in the above question we just had the nitrogen part, but here we will not only have the nitrogen part. Because of the presence of the excess O2, I will have this part here as well. Means we will have some excess air molecules as excess oxygen molecules as well, which have not been utilized for the combustion because of the lesser amount of the fuel, or you can say because we have provided the excess amount of the oxygen during the combustion process. So we will have this 0.75 ATH times of oxygen molecule here as well. Then again we will have the nitrogen part as well, but again you will see that this 3.76 times of ATH was at that time when we had the stoichiometric amount, but when we have provided the excess air, so it means that I will also have to incorporate this 1.76 molecules in determining the number of moles of the oxygen number of moles of the nitrogen as well. So this is how the equation for the second question will appear. And again you can see that we have only one unknown variable here, and that is the amount of the stoichiometric, that is the value of the ATH, which is the stoichiometric amount of the oxygen which would have been required here. But since we have provided the 75% excess here, so I have utilized 1.75 along with the ATH as well. I hope all of you guys would have understand the difference between the first and the second question. Now again moving forward, next step was of balancing the oxygen. Again you can see that in this question I have again utilized the balancing of the oxygen molecule, but you can also solve it with the balancing of the oxygen atom as well. So here I'm just going to solve it with the balancing of oxygen molecule. Now you can see here that I have 1.75 ATH moles of oxygen on the left side. So I have written down this 1.75 moles of ATH. Whereas on the right side you can see I have 3 moles of oxygen molecules. One carbon dioxide requires 2 atoms, means 1 mole of oxygen, 1 molecule of oxygen. But 3 carbon dioxide molecules will require 3 molecules of oxygen, means total 6 atoms of oxygen. So since I am balancing the oxygen molecules, so I have written down 3 molecules of oxygen. Here I have 4 molecules of water vapor in the combustion product, and 1 molecule of water has 1 oxygen atom. So 4 molecules of water will have 4 oxygen atoms, and 4 oxygen atom means that I have 2 molecules of the oxygen, and as I have explained earlier that you can either balance it by using the oxygen atom, or you can balance it by using the oxygen molecule, and I'm balancing this question with the oxygen molecule. So I have 3 molecules of oxygen in carbon dioxide and 2 molecules of oxygen in water vapor, which I have mentioned, I have written down here. Then we have this 0.75 times 0.75 ATH, which is the excess amount of the oxygen, the excess amount of the air which was provided during the combustion process. So this is what I have written down here. And then we just had the nitrogen molecule, and we didn't have any oxygen in that part, so we have just left it there. Now, solving this equation to obtain the value of ATH, we will get the value of 5. Then I will substitute. Then the next process is just same as I explained in the earlier question, in the first question. Now I will put this value of 5 in this equation, and when I multiplied this 5 with the 1.75, I will get the value of 8.75 molecules of air. Then I put this value of 5 here, and when I multiplied it with the 0.75, I get the value of 3.75 moles of oxygen. Similarly, I get the value of actual number of moles of nitrogen which we obtained in the combustion, that is coming out to be 32.9 moles of nitrogen. Since I wanted to determine the air fuel ratio, I explained earlier that I have to determine the mass of the air, and I also have to determine the mass of the fuel. So in order to determine the mass of the air, what I need to do is I have to multiply the number of moles with the molecular mass of the oxygen. The molecular mass of the oxygen is 29, and it is a constant value, so I have just placed it like 29 kilograms per kilomoles. Now in order to determine the number of moles, here you can see that I have basically 8.7 moles, and if I compute this oxygen, if I compute this number of molecules which are present in the air, and it is coming out to be total of 4.76 kilomoles, and when I multiplied it with the 8.75, I will get the actual number of moles of the air which is being utilized during this combustion process. So I simply multiplied this 8.75 with the 4.76, and then with the molecular mass of the oxygen, that is 29, and I divided with the molecular mass of the fuel, that is propane, C3H8. I multiplied the carbon atom atomic mass 12 into 3, since I had 3 atoms of carbon, some 8 atoms of hydrogen, multiplied it, so I multiplied 1, which is the atomic mass of the hydrogen, with the 8, and I will get the value of the air fuel ratio, and it is coming out to be 27.5 kilograms of air per kilograms of fuel. So that is how all the questions in the topic of this combustion is going to be solved. You can see that we had the almost similar amount of the same method which we followed in the first and the second problem, but in the second problem there was only difference of the excess air, and I have explained that part as well, that how we are going to utilize this amount of the excess air. Now moving forward, in the next question you can see that I have propyl alcohol, that is if I have this is question number 15.19. Okay, so again this is a bit different from the previous two questions, so I will explain this question in the later video. I'm moving forward towards the next question, and that is of the 15-16. I will first solve the question that is 15-17. I will first solve this question. So again, for example, if I have ethylene which is C2H4, and it is being burned with 200% theoretical air. By the word 200% theoretical means theoretical air means that we have 100% of the excess air. Means we had a certain amount of a theoretical air which was required for the combustion, and we have provided another amount of the theoretical air. That is what 200% of the theoretical air means we have provided the double amount of the air which was required for the theoretical combustion. Means we have provided 100% excess here in this for the combustion in this question. Assuming the complete combustion means there will be the no formation of carbon monoxide. Determine the air fuel ratio. So it is the same question just like the previous one which we solved, that was the 15-14. Now coming towards the solution, I will not spend too much time on this question. I will quickly explain this question and then move towards the next question. Here you can see that in the previous question 15-4 I had 75% of the excess air, so I mentioned 1.75 times of ATH, but here we have 200% amount of the theoretical air, or you can say 100% of the excess air. It means that we will have 2 times of ATH. 1 times of ATH means the theoretical amount of the air, and 200 times of ATH means we have 200% of the theoretical air, or we can say 100% of the excess air, means additional amount of the air which is being provided for the combustion process. Now I have written down the complete equation here. Since in the previous question we had 75% extra air, here we have 100% extra air, so I have not written down 0.75, I have only written down as ATH, molecules of air, oxygen. Now after the formation of this equation, what I am going to do is I am going to balance the oxygen. Again, you can balance the number of molecules and you can balance the number of atoms as well. I have balanced the number of molecules in this question as well. So here you can see I have 2 times of ATH moles of oxygen. So here they come on the left side. On the right side I have 2 molecules of oxygen atom. So here it is, the 2 molecules of oxygen atom, and I have 2 atoms of oxygen here. It means I had 1 molecule of oxygen, so I have written down as 1. And here I have ATH moles of oxygen, so just written down, I have written down ATH on the right side. So solve this equation to obtain the value of ATH, and it is coming out to be 3. Now the third step is to place this 3 in the above written equation and determine the actual values, actual moles of the oxygen, or actual moles for each of the reactant and product. This is what it is coming out to be. 2 ATH will make 6. This only ATH O2 will make 3 O2, and then if I multiplied these things by placing the 3 instead of ATH, I will get the 22.56 moles of nitrogen. Now again, since I have to determine the air fuel ratio, what I am going to do is I will have to determine the mass of the air and the mass of the fuel. So for the mass of the air, what I am going to do is I will multiply the number of moles with the molecular mass of the air. The molecular mass of the air is 29, and I will multiply it with the number of moles, and it is 6 multiplied by the 1 plus 3.76, which is 4.76. So 6 will be multiplied with the 4.76, and this number of mole will be multiplied with the MR, which is 29, to obtain the mass of the air. Next is to determine the mass of the fuel. and here you can see that we have ethylene, and I will simply multiply this 12 with 2 and 1 with 4. So we will add it to obtain the mass of the fuel. Then I will solve it to determine the value of the air fuel ratio, and it is coming out to be 29.6 kilograms of air per kilograms of fuel. So you can see that this question was very similar to the previous question, and there was only one difference, and that is of instead of having the 75% of the excess air, we had 100% of the excess air here. 100% of the excess air here. So here you means in the questions it can be written as that you have 175% of the theoretical air, means that you have 75% of the excess air. You can have 50% of the excess air or 150% of the theoretical air. It both means same, that you have 50% of the excess air provided for the combustion process. So I hope you guys would have understand these questions very carefully. So okay, now moving towards the next question. Now I'm going to start off with the question which is 15.9, which I left earlier, um, because the question number 15-17 was similar to that question number 15-14, so I thought it would be much better to explain these questions together. In this question you can see that we have propyl alcohol, and it is being burned with 50% of the excess air. You have to write down the balanced equation for the reaction if we have a complete combustion, and you have to determine the air fuel ratio as well. So means we have to do two things here: complete balanced equation and the air fuel ratio, which we are already doing in the which we have already done in the previous three questions. So okay, now moving towards the solution of this question, we have propyl alcohol. So here you can see that this is the propyl alcohol, C3H7OH, and it is being burned in the presence of the 50% of the excess air. So again, if I write down the equation for this question, I have propyl alcohol 7OH plus 50% excess air, means 1.5 times of ATH, and here I will write down this O2 plus 3.76 moles of nitrogen. Now here you can see that instead of writing 3 molecules of CO2, I am not writing down the molecules of CO2 yet, moles of the CO2 yet. We will have 4, we will have H2O, and then 50% of the excess air plus 0.5 times 3.76 ATH of N2. So here you can see I haven't written down the amount of the, instead of writing here this 0.75 ATH, I will not we cannot write here the 0.75 ATH. I will explain this part later. So here I haven't mentioned the number of moles of the compounds where I have oxygen in the combustion products. So the answer to that question is that here in the fuel we had oxygen molecule. So this oxygen molecule is also going to be utilized in the combustion. Therefore I cannot simply balance these combustion products which have oxygen molecule in it. So instead of just writing 3 molecules of O2 and 4 molecules of H2, I will mention I will write down here the moles in the form of a variable. Like here I have mentioned B with carbon dioxide, and like D with H2O, and E with O2. And here again in nitrogen as well I have written down F, but you can write 0.5 into this as well. Instead I'm just going to write it like F moles of nitrogen. So the reason because we are doing this here in this question, we are writing down each moles as variable in this question is because we had oxygen atom in the fuel molecule as well, and it is also we will also have to balance it, and we cannot balance it by just mentioning the actual number of moles which would have formed. So after the formation of this equation, what we are going to do is, the next step in the previous questions was to balance the oxygen, but here we will not only balance the oxygen, in fact we will balance the carbon atom, we will balance the hydrogen atom, and we will also balance the nitrogen atom as well, in order to determine all the unknown variables. I hope it is understood to all of you. So here if I balance the carbon, you can see that on the left side I have C3H7OH, means I have 3 atoms of carbon, whereas on the right side I haven't mentioned the carbon atoms. So you can simply say that B is basically equal to 3, means we will have to put 3 here. The value of B is coming out to be 3. So if I write down the equation by substituting these unknown variable, so instead of B, here you can see I have mentioned 3 times of carbon dioxide molecules. Okay, next step is again to balance the the hydrogen atom. I have 8 hydrogen atom here, whereas I had 2 times of D atoms in the right hand side. So 8 is going to be equal to 2 times of D, and the value of the D is coming out to be 4. So here again you can see I have written down the answer, and that is 4. Now here you can see that we had excess oxygen of in the left hand side we had excess oxygen of 50%. So the overall moles was coming out to be 1.5 times of ATH. So this 1.5 times of, and you can again see in this question I have 1 atom of oxygen in the fuel as well. So here it is preferable to balance the atoms of hydrogen. So I have 1 atom of hydrogen in fuel plus 1.75 times of ATH, and again multiplied with this 2, since we are talking about the hydrogen atom, not hydrogen, since we are talking about the oxygen atom, not oxygen molecule. So this 1 plus 1.7 times of ATH multiplied with the 2 in the left side, whereas on the right side you can see we have, since we are balancing the oxygen atom, so we cannot simply write here B, we will write it as 2 times of B plus B, since we have only 1 atom of oxygen in this water molecule, and here again we will write 2E instead of writing only E, since we are balancing oxygen atom. So we have this equation in the form of unknown variables ATH and E, since we already know the value of B and D. Now if we balance the excess oxygen only, you can see that we have 0.5% of ATH times equal to 2 times of uh, equals to the excess oxygen, and that is 2 times of E. Then if I balance the nitrogen, and it is coming out to be 1.5 times of ATH into 3.76 times on the left side, whereas on the right side it will become F times. So I have these equations in the form of unknown variables, and when I simultaneously solve these equations, in the first equation I have unknown variable ATH and E, and in the second equation as well I have unknown variable ATH and E, and then I have F, which is dependent on ATH. If I simultaneously solve this equation, I will get the value of E, which is 2.25, I will get the value of F, which is 25.38, and I will get the value of ATH, and it is coming out to be 4.5. Now replacing all of these unknown in the above mentioned equation, I will get the balanced equation, and it is coming out to be C3H7OH plus 6.75 times of O2 plus 3.76 times of N2. Then we had the 3 molecules of carbon dioxide, 4 molecules of a water vapor, and 2.25 molecules of excess oxygen. And then I had 25.38 molecules of the moles of a nitrogen. Now in order to determine the air fuel ratio, I will simply determine the mass of the air and the mass of the fuel, and it is the mass of the air can be obtained by simply multiplying the number of moles with the molecular mass of the air, which is 29, and the number of moles can be obtained from this balanced equation, and it is coming out to be 6.75 multiplied by the 1 plus 3.76, which is 4.76 moles of the air. And in order to determine the mass of the fuel, I will simply determine the molecular mass of the fuel, and since it has only 1 mole, we are talking about the combustion of 1 mole of the fuel, so I will have to multiply it 1, and it is not necessary to write that 1 mole. So instead of writing that mole into molecular mass, I have just written down the molecular mass in the denominator. So after dividing it, I will get the final value of the air fuel ratio, and it is coming out to be 15.51 kilograms of air per kilograms of fuel. So I hope these questions are clear to you. I have explained 4 questions so far, and I hope you guys would have understand all these problems, all these questions, and you would not have any queries regarding these questions. Okay, now moving forward towards the next question, that is 15-16. Here you can see we have solved question number 15-13, and we solved question number 15-14, and after that we solved question number 15-17, because this question was similar to question number 15-14, and then we solved question number 15-19. Now we are going to solve this question number 15-16. In this question you can see that 1 kilomole of ethane is burned with an unknown amount of the air. Means we do not know that we have a stoichiometric amount, or we have 150% of the theoretical air, or we have 75% of the excess air. So we do not know anything about it. So it means that the number of moles which we will use here is only going to be A, not ATH, because we do not know the theoretical amount. We do not know anything about the molecules. So an analysis of the combustion product reveals that the combustion is complete, means we have carbon dioxide and water vapors, and there are 3 kilomoles of free oxygen in the product, means we have 3 kilomoles of free oxygen, means which is not being utilized in the combustion. So we have to determine the air fuel ratio, and then the percentage of the theoretical air which is being used here in this question during the combustion process. So now forming the equation for this question. Now here you can see that we have ethane, yes, ethane as a combustion fuel, as a fuel. So this ethane, and when we add this unknown amount of the air, because we do not know whether we have a theoretical amount and how much excess amount of the air. So instead of writing ATH or 1.75, I have just written down it as A. We do not know anything about it. We have to determine this. And as a result, we will get two molecules, two of carbon dioxide, three molecules of water vapor. And it is mentioned in the question that we have excess 3 kilomoles of free oxygen available in the combustion product. It is mentioned in the question. So this 3O2 is basically the excess of free oxygen which was available in the combustion product. And then again, nitrogen is 3.76 times of A. So balancing the oxygen molecules here, again we have simply A on the left side and 2 plus, again you can write it as 3 upon 2 or simply as 1.5, because we are balancing the oxygen molecules. So we have 3 atoms here, so you can write it as 1.5. But if you are balancing the atoms, so in the left side it will become 2A plus 4 plus 3 plus 6. Since in this question I have balanced oxygen molecules, so it is A plus 2 plus 1.5 plus 3. And when I solve it to obtain the value of A, it is coming out to be 6.5. Now substituting all of these values, now if I substitute all of these values, the value of A in the above written equation, I will get the balanced equation, complete equation for this reaction. And in order to determine the air fuel ratio, what I need to do here is I have to determine the mass of the air and simply divide it with the mass of the fuel. And mass of the air can be determined by multiplying the number of moles of the air with the molecular mass of the air, which is 29. And the number of moles of the air can be determined by simply multiplying this 6.5 with 1 plus 3.76, which is 4.76. So 6.5 multiplied by 4.76, this is the number of moles with the molecular mass, that is 29, and divided with the mass of the fuel. So simply determine the molecular mass of the fuel, and that is 2 times of 12 plus 1 times of 6. So the air fuel ratio is coming out to be 29.9 in this case. So the next part was to determine the theoretical percentage of the air for this question. By the word theoretical percentage, it means that we have a stoichiometric the stoichiometric amount of the air during the combustion process. So I have to again solve this equation by, instead of writing A, I will write ATH here, and I will not have any excess air in the combustion product. So here you can see in the second equation we do not have any 3O2 part, because 3O2 was only present during the actual process, and we are talking about the theoretical part here. So again solving this, so after formation of this equation, I will balance the oxygen, determine the value of ATH, and it is coming out to be 3.5. Then in order to determine the percentage of the theoretical air, what I will do here is I will simply divide this 6.5, this A, the actual amount of the air which was being injected, which was entered into the during the combustion process, to the and divided with the theoretical amount of the air which is being required for the complete combustion. And here after dividing it, 6.5 divided by 3.5, I will get the value of 1.86, and for the percentage I will multiply it with the 100 to obtain the value, and it is coming out to be 186 percentage of the theoretical air. Means I had provided 86% of the excess air during the combustion process. So this is what these questions are all about. So far I have explained 5 questions, 5 numericals. I hope these questions are quite clear to you. Now moving towards the last question of this topic. This is quite a practical question, because we have the implementation of the this combustion process in the industrial fired boiler. Boilers are one of the most uh, widely used equipment in the industries for the heating purposes. If we are talking about a power generation sector, to obtain the steam which will drive the turbines. If we are talking about a process industry like a textile industry, it will provide you the steam which are necessary, which are desired for the process. So boilers are more or less utilized in most of the industries. So in this question it is mentioned that you have a natural gas fired industrial boiler. Natural gas means we have methane, which operates with an oxygen concentration of 3 mole percent in the flue gases. This is an important factor here. 3 mole percent means we are talking about the mole fraction here. Determine the operating air fuel ratio and the equivalence ratio. Treat natural gas as methane. I explained earlier that natural gases are usually treated as methane. So we have to determine two things here, the operating air fuel ratio and the equivalence ratio. Means I will also have to determine the theoretical air fuel ratio and simply divide them. So moving towards the solution of this question, so CH4 plus A times of O2 plus 3.76 times of N2, since I did not have any information regarding the amount of the air which is being utilized here, so I have just written down it as A. Then in the combustion product I will get CO2 plus 2 times of H2O, and then here you can see that I have B times of O2, which is the excess air which we will have in the combustion products. So it was mentioned in the question that here you can see that oxygen concentration is 3 mole percent in the flue gases. That in the flue gases we have some percentage of the we have some amount of the oxygen, free oxygen as well. So that is why I have written down this B times of O2 in the equation. So everything will be given in the question, and you have to extract the information from the question. This is what these questions are all about. And then I will have 3.76 times of A moles of nitrogen. So if I balance the oxygen atom here, 2 times of A in the left side equals to 2 atoms of oxygen in carbon dioxide and 2 atoms of oxygen in each molecule of water vapor, and then I have 2 times of B. And if I simply balance this equation, I take the 2 as a common in the right side, and then 2 and 2 would be cancelled out with each other. I will get and rearrange this equation to obtain the value of b, and it is coming out to be a minus 2. So this is the equation which we will get by obtaining the by balancing the oxygen. So the next thing which was mentioned in the question, and it is very important thing for the solution here, is that 3 mole percent of oxygen is present in the flue gases. So I will utilize the intermediate concepts of the mole fraction here. So the mole, we studied about this, that the mole fraction of any molecule would be the molecule of the number of moles of that gas divided by the entire molecules of the mixture. So if I have to determine the mole fraction of the oxygen, I will simply take the ratio between the number of molecules of oxygen with the number of molecules of the entire mixture of the gases. So here you can see in the combustion product I have B moles of oxygen, so B in the numerator, and in the denominator you can see I have 1 mole of carbon dioxide, 2 moles of water vapor plus B moles of oxygen, and 3.76 times of A moles of nitrogen. So in the denominator I will get 1 plus 2 plus B plus 3.76 A. And since the mole percentage was given 3%, if I convert it into the fraction form, I will get 3 upon 100, which is 0.03. So this 0.03 is equals to A minus 2, which I explained earlier, that B, which we get earlier by balancing the oxygen, that B is equals to A minus 2. I replace it in this equation, so I get A minus 2 upon A plus 1 plus 3.76 times of A. And when I solve it to obtain the value of A, I get 2.368 times of A. So I hope it is clear to all of you. And if I want to determine the value of B, I will simply put the value of A in this equation 1 to determine the value of B, to determine the excess moles of the oxygen present in the combustion product. So to obtain the air-fuel ratio, what I will do is I will simply multiply the number of moles with the molecular mass. The molecular mass of the oxygen is 29, and the moles are this A multiplied with 1 plus 3.767, which is 4.76, multiplied with 2.368, which is the value of A. And in the denominator we will get the molecular mass of the fuel, which is CH4. So 1 molecule of carbon, which is 12, whose atomic mass is 12, plus 4 atoms of hydrogen multiplied by the atomic mass of hydrogen, which is 1. So as a result we will get the air fuel ratio, and it is coming out to be 20.4. So in the next step it was asked that you have to determine the equivalence ratio as well. So as I explained earlier in the previous classes as well, in the topic of the carburetor, I have explained this this equivalence ratio in quite some detail. That equivalence ratio is basically the amount of the it is basically the stoichiometric air fuel ratio. It is the ratio between the stoichiometric air fuel ratio to the actual air fuel ratio. So I have one unknown variable here. I have determined the actual air fuel ratio, which is coming out to be 20.4, but I haven't found out the stoichiometric air fuel ratio. So again I have to solve this question, and in that question I will not have this excess air, which is B times of O2, and that question, and if for the theoretical air, if I solve this question, it will become just like the first problem which we solved, like this, and as a result I will get this equation. Then I will determine the air fuel ratio, and it is coming out to be 17 point it is coming out to be 17.3, or you can say 17.26, approximately it is same. So this section, this portion was similar to the question number 1 which we solved, which was 15.13. So I haven't solved that part again here. I have simply written down the how did we calculate the stoichiometric air fuel ratio, but I mentioned that you can solve this, you will solve this part as it was solved in the first question 15-13. Then after solving it, since we have to determine the equivalence ratio, I will take the ratio of the stoichiometric air fuel ratio with the actual air fuel ratio, and I will obtain the value of equivalence ratio, and it is coming out to be 0.846. And it is mentioning, it is explaining that we have a lean air fuel mixture here, since the amount of the air entered in the actual process is quite high. And I also explained that for the in the topic of the combustion, I explained that for maximum flame speeds are occurred when the equivalence ratio is about 1.1 to 1.2, means the mixture is slightly richer. So here you can see the mixture is slightly leaner, and since the equivalence ratio is less than 1, it means that we have a lean air fuel mixture here. And you can see it from the question as well. We had excess oxygen which was found in the combustion product. It means that we provided the extra amount of the oxygen. So this was all from my side regarding the combustion topic. I hope you guys would have understand all the theoretical part, and must have understood the numerical sections as well. In case you have any query regarding the numericals, just note down your questions. You can ask me in the video in the online session, and you can ask me through a WhatsApp group or in the Google Classroom as well. From the next class we will start off the new topic. Till then, I expect you to watch these videos carefully and try to understand the basic concepts regarding these topics. So till next video, Allah Hafiz.